Since I'm anyway, is this on? Yeah. Since I'm anyway standing here, I was going to continue with telling what I'm planning to do in my afternoon session, but just sort of the general idea. I just lost my mouse here. Where is it? And this is actually a presentation that I gave a few months back that has all the figures that I want to sort of go through, that I used when I was visiting the group in Jena, where they had a different summer school last week. And there I was talking about data cubes. And that is essentially also what the afternoon session will be about, in particular about raster and vector data cubes. So data cubes. Data cube is a very old concept. It's basically the idea that you usually put data in a table, sort of you have records and you have columns of the same type and records are your observations. But quite often things are sort of aligned by certain axes, so to speak, that give a natural organization of the data. So the original idea comes from OLAP, data cubes, online analysis, processing things, where they said, okay, we have like sales data, where we have for every warehouse, we have a number of products, and then sales of these products for every day of the year, for instance. Yeah, so you get kind of a cube where one axis is the warehouse, where something happens, the other one is what is being sold, and the other one is sort of the time when did happen. So that's already three-dimensional. And then you could have more variables like who sold it, right? That will be another axis. You have a four-dimensional cube. And so these data, and you can of course put it in a long table, but quite often you want to do aggregations per warehouse or per day or per product. And if you don't have them in a cube, things get actually much easier. And a lot of these things have a spatial aspect in them, right? A warehouse is, of course, a spatial location, right? Even if you don't know the location, it is one, but it could be implicit. So what are data cubes? The formal thing is essentially they are arrays, and arrays basically map dimensions to attributes. And dimensions are kind of things that could either vary continuously or be discrete, right? So warehouse could be a discrete dimension, and then time would be something that is ordered, right? That is continuous, but then you get daily totals or something like that. And then the attribute would be the amount of whatever money or the amount of items sold or something like that. So this is kind of a mapping from dimensions to attributes. So arrays are enumerated sets. They may represent sets of entities or discrete or continuous variables, spatial dimension, time of day, frequency or wavelength, or duration. Those are kind of things that you could put into dimensions, and where you would have a set of attributes associated with that. So we use the word cube here as it's a cube, but it's not a cube, right? The cube is just the metaphor, really. So a real cube would have three dimensions. But if we say cube, we mean anything also more than three dimensions, but also things less than two dimensions, right? So also things that only have a mapping from one dimension to an attribute, which is essentially a simple table, is also a special type of a cube. And so that makes it very, very generic. So one-dimensional data cube could be a table with records, like a data frame or a table or something like that. And of course, you can also store all the data in a cube in a data frame, but then you need to sort out everything, right? The structure is really lost. So spatial data cubes refer to data cubes with spatial dimensions in several ways. And one is that you map basically a really spatial dimension like X, Y, or Z onto, into sort of regular grids, which give you the standard raster data. So there the index space is continuous, and you get an implied sort of half-open interval. And every coordinate really maps into a unique ID, into a unique index, and that also means that all spatial dimensions map into a single. And another alternative, so this is one possibility where one sort of X, Y, or Z map into a dimension index, and another one is that all spatial dimensions map into a single cube dimension. Where I gave the example of the warehouses. You have one dimension, which is the warehouse, which has an idea, but also a location, right? And it's not like the organization is organized in some way, but it still maps into one cube dimension. So a cube dimension really is a set of whatever it is, features, points, lines, polygons, or something like that, right? So that is also a case that is what we call a vector data cube. We can also have combinations. For instance, we have regions. You have sort of regions along one axis and regions along another axis. And in our cube, in our matrix, we put sort of how many people went from this region to that region, yeah, which would be an origin-destination matrix with the regions. Yeah, so then we have a spatial data cube where polygons appear twice along 2 dimensions. And then we could do that by hour of day, and we get a 3rd dimension, and so on. So it's not like time has to, space or time has to happen only once in the data cube. You could have cases where you want to represent flows, where you do it twice. So this is the classical image of a spatial data cube where we have longitude, latitude, or x and y, and we have a time sequence of some kind of imagery, satellite imagery, or something like that of a single band would be the typical example. Then, of course, we have typically more than one band. So we have n bands. Sentinel-2 has like, I think, 13 or something like that. And then we have a time sequence of those. And we can have different sensors, right? We have 2 Sentinel, 2 satellites, but we could also say, well, this is Sentinel and this is Landsat, right? We have like 2 different sensors giving us very similar data, and hopefully these bands match and so on. So this would then already depict a 5-dimensional data cube, where we would say, okay, we have x and y, 2 dimensions, time the 3rd, then the color is the 4th dimension, and the sensor could be the 5th dimension. Yeah, it's a 5-dimensional data cube. And for vector data, you could have something like this, right, where we have for regions in a particular country, we have here a time series for every region, for instance, land cover over a couple of classes, which could be another dimension. So we have a 3-dimension vector data cube, where, of course, space in this case only takes 1 dimension, and time also 1. And you could also do that for points, and you get these kind of images. And then you have this issue, like what do we do with this data? And there we have sort of without end all kind of ways how we go from raster to vector and vector to raster. And examples are, for instance, that you have some climate model and sequence of some climate parameter over an area. And for the particular points, for instance, you study some cities in particular conditions. You want to sort of extract the values there. So you want to get point time series for these places. Or you would aggregates for, you have regions over which you want to find out what a maximum is or what a mean temperature is and how that develops over time. These kind of operations happens a lot. You can go the other way around. You can polygonize things. So if you have raster, you can represent them by contour lines, for instance, if it's something continuous. Or you could just draw the contour around an area that has a continuous categorical value, like the contour around a certain area with a certain length use. And you could continue working with it as polygon data. Vector to raster gives you rasterize or interpolate or finding densities of a point pattern. So these are typical operations that happen there. And then we work with different raster types. We have sort of the 3 that GDAL can work with. We have rectilinear, irregular, that we run into a lot when we look at what climate modelers do. They tend to sort of ignore the usual convention that grid cells should be equal everywhere. And we have curvilinear grids, which is the typical thing. If you would have raw satellite data, it's basically one of these stripes with this funny shape, basically, because it's rotating around the Earth. So this is kind of how it's kind of the raw data comes, and then somebody cooks it up for you and hopefully transforms it into something regular that we can handle it. But it's not like you don't run into these regularly or so. In the contrary. So there's the R package. Raster, that has been legacy and does a lot of things. I will discuss that a little bit. And there are also R arrays. Yeah, so you can handle array data in R without problem in base R. But it has limitations in the sense that it can put labels along dimensions. It can put labels along dimension values, like here, row and column names and so on. And level names can all be sort of named. But you can't put really times in there or spatial features or coordinate reference systems. So it's very limited. You can put labels, but it's very limited in terms of properly handling data there. So the way we worked around it is basically writing a package that is called stars. and that basically uses these arrays, but then extends that with metadata information about where your space and where your time goes. Essentially, that's what it does. So this is what I'm going what we're going to look at. Another thing that I'm going to touch upon. There is sort of the problem. What do I have here of all kind of rasters that do not match? That is something that Marius will focus on, and luckily will give 2 sessions on about today. There's another activity where we have the issue of, okay, we have now this satellite data, but for instance, we want to look at all the Sentinel-2 data measured for the last 3 years over Europe, something like that, right? So we have a larger chunk, a larger area and time period, and then if you say, okay, let's download these data, then you go like, yeah, okay, right? Let's download. So you can sort of start it, and then you will find out that it will take sort of an infinite amount of time. So there's no way to do that really, because the data are too large, and network bandwidth is, even in universities, is too slow to reasonably do that. And we are working on a sort of a setup where we basically we sort of can do the computations using this view of a data, so using this concept of a data cube, doing the computation actually on the place where the data are, so that means in the cloud storage, in the cloud platform where these data are kept, where you can do these computations, where you have permissions to do these computations. And then basically the operations we do there, and then OpenEO is essentially a project that designs and implements an API for doing that, and the operations are very similar to what we kind of low level do with this stars package in a pure R small environment, but the ideas there are identical. So I will briefly discuss that, and on Friday there's a longer session where we will really work with the software that's being developed in OpenEO in conjunction with interactive environments and with our packages that can use that. So far, that's what I'm going to talk about. Questions? Questions come to the session. Marius, next? Good.